Hello, everybody, and welcome to Echo Live. Today we will be talking about static electricity, so thank you so much for joining us here for our next segment of Echo Live, coming to you from the Michigan Science Center. My name is Anna, and I will be leading us through some static electricity demonstrations today. Now, some of these experiments, oh look, we've got a stowaway hidden in my studio. Now, since we'll be talking about electricity and cats, just like people, are pretty good conductors, we're going to go ahead and put Keyboard the cat away somewhere safe where she's not going to be involved in our experiments. Hold on just one moment for me. Maybe we'll get her involved in some experiments down the road, but thank you so much. Cats don't make very good lab assistants, let me tell you. So today we'll be talking about static electricity. This is something that we all experience all the time. Static electricity is pretty easy to create. And of the different types of electricity that we talk about at the Michigan Science Center, static electricity is one of the safer ones. Now, I should preface with, we should never play with electricity at home. So before we start any of our science experiments here on our studio table, we're going to take an oath all together. Everyone raise your right hand. Even if you're sitting at home, this oath applies to you too. And repeat after me. I promise to never, ever play with electricity at home or anywhere else. Great. So now we've covered all our bases. That oath is legally binding, so you can't break it even if you want to. But we'll never want to play with electricity at home, especially the type of electricity that comes out of the sockets in our wall. That's a different type of electricity than the static electricity that we'll be working with here in the studio. And some of these experiments, I'll give you instructions for how you can safely repeat them at home. But remember, we are never playing with electricity. We are doing some safe experiments with electricity. So static electricity, what is it really? Now, electricity of any kind is described as the movement of electrons. If you're not sure what an electron is, we'll go ahead and I'm going to share an atom model with you. So if you were to get an up-close view of an atom, it would look something like this. In the center of our atom, we have what we call the nucleus. And the nucleus is overall positively charged. The nucleus is made up of both protons, which are positively charged, and neutrons, which are neutrally charged. They have no electrical charge. So the center of an atom is positively charged. What's important when it comes to electricity are these electrons. Electrons are negatively charged, and they are orbiting around the nucleus of an atom. Since electrons are orbiting the nucleus, they can actually be transferred between different atoms and be shared by different surfaces. So the easiest way to create electricity is just by rubbing two objects together to be able to get that transfer or that movement of these negatively charged ions that we call electrons. Here's an experiment that you are able to try at home. Using a balloon, we know what might happen if you were to rub a balloon on your hair. Go ahead, tell me in the chat feature what happens to your hair or possibly, your clothing, other sorts of fabric type materials if you were to rub this balloon on them. Go ahead, tell me in the chat, what do you know or what do you think is going to happen when I rub this balloon on my hair? I see some great answers. I see that we create static and my hair should start to stand up. Now, it might help if I kind of loosen my hair tie here and I'll go ahead and start rubbing this balloon on my hair. Now, you can see it's moving just a little bit. It might actually help if I remove my really awesome but kind of distracting green screen from behind me. Now, if I take that away, you can probably now see a little bit better that my hair is starting to stand up or starting to stick to the balloon. That's all because of that movement of electrons. When I rub the balloon on my hair, the balloon starts to take the electrons off of my body. Now, my hair is repelling away from me because it wants to be as far away from my other positively charged hairs. That's because electricity and magnetism are extremely linked. You really can't have one without the other. So when we generate an electrical current, there's also a magnetic field that is created. Now, if you think about magnets, if I were to take two north ends of a magnet, we know that all magnets have a north pole and a south pole. But if I were to take two magnets and try to put their north poles together, what would happen? Tell me in the chat. What would happen to our north poles once I try to stick them together? That's right. They will repel, or they push apart from each other. Now, some magnets will stick and some magnets don't, but when we try to stick two north poles of a magnet together, we say that they repel. In electricity and in magnetism, we say that opposites attract. So a north pole would attract a south pole, or a positive will attract a negative, but like charges and like poles on a magnet will repel or push apart from each other. When you take away all the negative ions off of my hair, all of my hair becomes positively charged. And so my hair wants to push and repel away from all the other like charged pieces of hair on my body. Now, if you'd like to try another experiment using our balloon in creating static electricity at home, all you'll want to do is rub that balloon on your hair and test what kind of effects we see using different household objects. Now, our balloon is now negatively charged. It's taken the electrons off of my hair. So our balloon is negatively charged. If I were to place something like an aluminum can, which is neutral, since I've not done anything to the can, it still has its protons and its electrons. I can then bring our charged balloon near the can and we'll watch what happens. The can starts to move across the table, even though the balloon isn't touching it. That's because of that force of attraction. The balloon is negatively charged, and it is trying to attract to the protons that are still attached to this aluminum can. So they have an attraction since they are oppositely charged. You can do the same thing with something like a crinkled up ball of aluminum foil. So if we set the ball down on the table, charge our balloon back up, and we can get our ball to roll across the table as well. Amazing. I see a great question in the chat that says, why can static electricity not be produced in high humidity? That's because humidity or moisture in the air will actually knock some of those ions out of the air. So we don't see this effect as easily on a really humid day. So static electricity is much less in the summer, especially here in Michigan, when we have really high humidity. But in the winter, when the air is much drier, we see a lot more static electricity. Now, we have this device right here, which is a pretty cool device to generate static electricity. It's actually called a Van de Graaff generator. So what you'll learn in science, or what we've learned so far, is that scientists love to name things after themselves. This Van de Graaff generator was invented by a guy named Robert Van de Graaff, but it doesn't actually generate Van de Graaffs. We said it generates static electricity. The way that it works is on the bottom of our generator, we have a hand crank. And as we turn the crank, it's actually going to pull around this big rubber band, and it's going to start rubbing against a set of brushes up here inside the dome. That's going to generate that static charge. Just like when we rubbed the balloon on our hair, we saw movement of electrons. The same thing will happen as we turn the crank and rub the rubber band against the set of brushes. To be able to see this a little better, I'm going to set this behind my table on just a small platform here so we can get a more up-close view of our Van de Graaff generator. Now, static electricity in small amounts is relatively safe. We know that if we shuffle our socks on the carpet and we were to reach out and touch something metal, we might get a small shock, right? That's all because of that static difference, or that imbalance in static charge between those two objects. It's not going to be incredibly painful, but we can actually create that same static imbalance right here. So I'll turn the crank, generate a little bit of a charge on our dome, and then bring another object, a neutrally charged object, near it. Now, hopefully you can see that we're creating a small amount of sparks jumping between our Van de Graaff generator and this neutrally charged rod. So we'll charge it back up. and we're actually creating some small sparks. Now, if these were much larger, we might say that they look a lot like lightning. And really because that is the same thing. So lightning is created in nature when we have a static indifference between the clouds up above us and the ground, and that electricity wants to transfer between those two indifferent or differently charged objects, which creates a lightning strike. Now, I have a volunteer to demonstrate something pretty cool using our Van de Graaff generator. Unfortunately, Penguin Pete was not available for this demonstration, so I had to look somewhere else. And unfortunately, keyboard's not a great volunteer either. But if you'd like me to grab our volunteer, go ahead in the comments, give me a like, give me a thumbs up, give me a heart reaction. Let us know, do you want to meet our celebrity volunteer? She's someone you all know and have all heard of before. Let's see. All right, I'm gonna go grab her. All right, give a big round of applause for Barbie. Barbie is a great volunteer. If you have not heard of Barbie before, you should definitely look her up. Barbie is an amazingly talented woman, big role model in the STEM world. Barbie is an astronaut. She is a chemist. She's a veterinarian. Barbie loves science. Barbie loves science so much that I know she's not going to be upset that for this demonstration, we actually have to do this. Don't worry, we'll put Barbie back together at the very end. She's a very, very good volunteer and she doesn't mind. So we're going to take Barbie, or just her head really, and place it right on top of our Van de Graaff generator. If we think back to our balloon, right, when we create this static charge, we can see something kind of fun happening to Barbie's hair. So we'll zoom in on Barbie. And we're gonna start turning the Van de Graaff generator crank, and let's watch what happens to her hair. Now, the more we crank, the crazier Barbie's hair gets. You can see that it's starting to rise. If I crank a little bit more, we see even more movement. The principle is the same as what we saw with the balloon when it was rubbed on my hair. Barbie's hair is becoming positively charged, just like the charge on the Van de Graaff generator as the rubber band takes away its electrons. Since her hair and her body and the generator are all positively charged, her hair is repelling away. If I take a neutrally charged object like our discharge rod and put it near Barbie's hair, you see that all of her hair starts to follow the discharge rod around, since we are seeing that attraction, similar to magnets. If we want Barbie's hair to go back to normal, all we have to do is discharge the Van de Graaff generator by touching it with our rod, and her hair falls right back down into place. Now, we have one final demonstration to show off, but I'd love to pause for any questions you might have about our activities so far. So if you do have questions, please type them in the chat. I'd love to answer a few questions before our last demonstration. We'll pop Barbie's head back on, sit her down so that she can observe our last few experiments that we'll be doing here today, and I'll keep an eye on that chat. Now is also a great time for us to, as always, thank the sponsors of the Michigan Science Center, specifically the DTE Energy Foundation, and all of our other major donors are the reason that we're able to keep providing these free programs for you over Facebook Live and over Zoom every single weekday at 2:30 p.m. Eastern. The Michigan Science Center is a nonprofit, and we do rely heavily on our membership sales and our ticket sales normally to generate revenue and to keep us providing programming for the public. So if you are enjoying Facebook Live, please continue sharing these videos over your Facebook, invite other students and other families to join in, and also please consider making a donation to the Michigan Science Center through our website. That link will be posted with this video once it ends. So thank you to all of our sponsors, including people like you who just love science and are joining in from home. Now let's look for some questions. See some questions in our Zoom chat here. Can static electricity ever hurt you? Absolutely. Even though static electricity is something that we experience all the time, and it's pretty easy to generate using safe objects like balloons or like the carpet underneath on the floor, we never want to play with electricity. We always want to have a healthy respect for it. Strong or high-powered electricity can be very, very dangerous, especially electricity like the stuff in your walls that can come out of the walls or come through your body. But static electricity is what we call a high-frequency alternating current, meaning that it flows over your body to get to the ground instead of through it. That's part of the reason that many people survive being struck by lightning, but electricity in any form can be extremely dangerous. Great question. Let's check on our Facebook comments. Why did all of her hair not go down? Part of it has to do with Barbie's hair isn't made out of real human hair, so it kind of stays up just a little bit longer since it kind of will hold its shape. But slowly, as like we said, the humidity in the air will start to knock off some of those charged ions, and her hair does eventually fall back into place. Great question. How much static electricity does this machine produce? That's a great question. This Van de Graaff generator can actually produce about 50,000 volts of electricity. But the amperage is pretty small, so it's not very dangerous by any means, but it does produce a pretty high voltage count of electricity. What would happen if we put the balloon on the Van de Graaff generator? That's a great question. We can actually try that if we'd like. So we'll take the balloon, hold it near our Van de Graaff generator here, and then we'll start turning the crank. And you'll notice not much is really happening. Since the balloon isn't touching the Van de Graaff generator, it's not copying that same charge. And balloons, unlike people, are not very good conductors. So since they're made out of rubber or latex, they aren't great at conducting electricity. So it's pretty hard to generate a shock using the balloon. And so we don't see much of an effect using that, but that's a great experiment. Again, keep trying some of these things at home. And as you see, I just got too close to the Van de Graaff generator, and it gave me a small shock on the shoulder. Can you do this experiment with something other than hair or the carpet? Yeah, absolutely. So your clothing, especially specifically cotton clothing, is also pretty good for generating this charge. So if you have any sort of object that you want to just rub on various pieces of material, you can try using your t-shirt, try using your couch. You could even try using objects in your house like the walls or a placemat on your table. Try different experiments using different materials and see what kind of levels of static electricity you can generate. Remember that you might give yourself a small shock depending on what you're using, but the amount of electricity that you'll generate by rubbing a balloon or another small object should not be enough to harm you. So feel free to experiment, but always do so safely. All right. Are there atoms being transferred between the two? No. So atoms are the entire atom that we would have seen in that diagram, including the protons and neutrons. Atoms are what make up matter. So we didn't actually see any transfer of entire atoms, but we are seeing the movement of those electrons. Since they exist in those outer shells, we can show that diagram again. Since they exist in those outer shells, they're much farther from the nucleus and they're not as tightly attached. And that's the reason that if another atom were to come in, it could actually borrow or transfer one of those electrons onto another atom, which would leave this atom with a different charge than what it started with. It would have a positive charge and the new one would have a negative charge. But electrons are the things that are transferred when we're talking about static electricity. Now, I'll check back for more questions at the very end here, but we do have another experiment I'd like to try. Now, I also brought with me something that we call a Tesla coil. So if you've heard of Nikola Tesla, he did a lot of amazing work with electricity. He invented something called a Tesla coil in order to bring free wireless electricity to cities and to homes. Now, adults, if you're watching, you know that we don't have free electricity. So unfortunately, Thomas Edison, who worked on electricity at the same time as Tesla, kind of won that battle. And so now we pay for electricity to travel to our house through wires safely, either above or below the ground. but you're going to find out why. So I have a small version of a Tesla coil that's actually handheld using this device right here. So this is a handheld Tesla coil. Inside it, it's just plugged into a 120 volt outlet, just like all the outlets that you have in your home. But it's actually going to amplify or pressurize that electricity. And then when it comes out the end of the Tesla coil here on this metal rod, it's going to be about 50,000 volts, just like our crank generator here. Now, if we zoom on the table, I can actually show you the electricity that is produced using this handheld Tesla coil. So if we take something that's decently conductive, like this empty can here, and then we hold our Tesla coil near it, let's see what happens. We see big purple sparks. So you can create almost up to 3-inch sparks using this small version of a Tesla coil. So Tesla wanted to give us free wireless electricity. You'll notice that I hold this near this can, the electricity is being transferred even without touching the can. So that electricity is now, when it's on, it's covering the can because we said it is a high frequency alternating current. It's flowing over the can, not through the can. Just like if I were to turn on the power into a low enough amount, you can't actually zap your own skin. And that's not incredibly painful. We said that this is just, again, one of those static shocks. So it's not incredibly painful, although it is a bit shocking. Science joke for everyone, keep them on their toes. But that only works with things that are conductive. So if we use something like plastic, just like our balloon, we don't really see those same static sparks. So even if I were to touch it, nothing happens. So you really need something that is a good conductor. To show you how this wireless electricity would work, we do have a light bulb here. So a light bulb not attached to any sort of power source. You can see both ends are open. They're just taped off for safety. I'm using electrical tape. And then we'll go ahead and I will turn on our Tesla coil. Watch what happens to the light bulb. Turn our power back up just a little. Now these Tesla coils are pretty loud, so we can tell why we don't use these to power up our homes or city, even though it does work, right? We do see that even without touching this light bulb, we can send the electricity wirelessly through the air in order to turn it on or make it start lighting up. Now, we do have a Tesla coil at the Michigan Science Center that is really, really big. It's about 6 feet tall, so taller than I am, and it shoots amazing lightning bolts about the size of our DTE Energy Sparks Theater. One of our guests to the Science Center actually caught a pretty cool video of our Tesla coil. So I'll play that video for you here today, and then we'll wrap up with some final questions. So here is the Michigan Science Center's giant Tesla coil shooting lightning bolts the size of our room.
Here we go with our Tesla coil in 3, 2, 1.
I highly recommend that if you've never been to the Michigan Science Center, you come check us out. Come see our free electricity show that happens in the DTE Energy Sparks Theater so you can see our giant Tesla coil. Now, when you do get to experience it live, you'll know exactly what I mean, that these Tesla coils are extremely loud. So loud that we really wouldn't want to have them on every street corner in order to power up our towns. And they also produce something called ozone. So if I smell my hand, that I used or that I zapped with the Tesla coil, I've actually created a small amount of ozone, which is O3 in its chemical structure. In a small amount, like the amount we've created here, the amount that our giant Tesla coil produces is not unsafe by any means. But if we had thousands of Tesla coils on every street corner in order to give us power at home, that amount of ozone would be really, really bad for humans. Unfortunately, ozone is only good for us way up high in the atmosphere to protect us from the sun's UV rays. But down here on Earth, it's not so great. We don't want to breathe in ozone all the time because it can give us all sorts of health problems surrounding our lungs. So that is about the end of our show here. Thank you guys so much for joining in. We are really enjoying bringing these programs to you every day. are every weekday at 2:30 p.m. Eastern. Again, if you enjoyed this video, please consider sharing it on your Facebook page so we get even more people in on the fun tomorrow. We will see you back here tomorrow at 2:30 p.m. Eastern, either on the Michigan Science Center's Facebook page or through the free video conferencing program Zoom. If you're looking for some experiments that you can try at home, our website is live. Our website is listed here on the bottom of the screen. So it is www.mi-sci.org/at-home-science. We'll be posting experiments that you can and you should try at home that are safe, and that we would love for you to tell us how your experiments went even after our Facebook Live events end. So thank you everyone so much for joining us here today. We hope we'll see you back here tomorrow. Tell us how we did in the chat, and have a great rest of your day.